Hi, my name's Matt Benedict.
Hi, I'm Brian Lowe.
Hi, my name is Zachary Spencer.
And this is our Dynamics project. For our dynamics problem, we are given a clamp with mass equal to mb and a hoop with its mass equal to mh. And the hoop's mass is equal to 3 times the mass of the clamp. Also, it was released from rest when theta is equal to 90 degrees and there is no sliding or slipping. For our problem, we were supposed to find A, the angular acceleration of the hoop, and B, the horizontal and vertical components of the acceleration of B. For the free body diagram of the hoop, we have the angular acceleration of the hoop. We have the acceleration at A, and we have the acceleration of B in the x direction, as well as the acceleration of B in the y direction, which is tangential to the curvature of the hoop. Given the free body diagram, we can use kinematics and figure out the acceleration of B in the x direction is equal to radius times the angular acceleration, and the same for acceleration of B in the y direction.
For our next free body diagram, we have the hoop and the clamp, and we're showing the forces here. In the middle, acting on the center, we have the weight of the hoop. On the right at B, we have the weight of the clamp, WB. At point C on the bottom, where it makes contact with the surface, we have the force of friction and the normal force that's acting on the hoop. And that free body diagram is equal to, for the kinetic diagram, we have the mass times the acceleration of the clamp in the x direction and the y direction, the mass times the acceleration of the hoop, which is acting on the center, and I times the angular acceleration of the hoop. And I equals mh r squared. And since we know that mh equals 3 times the mass of the clamp, I equals 3 times mb r squared.
For our equations of equilibrium, we decided to use a moment around the point C at the base of the hoop where it contacts the ground is equal to the kinetic moment. As you can see right here in these diagrams, for the moment around C, the only force acting on it is the weight of the clamp at a radius of r from the perpendicular to the point C. And for the kinetic diagram, we have the components of acceleration at point B right here, with the only x component of acceleration at the center of the hoop, as well as the moment of inertia times the angular acceleration, which acts over the entire hoop. All of these quantities, with the exception of the moment of inertia, are also a distance of r away from point C. As you can see, we added r in here, and this can all be equated to all these values here, which we inserted from these two, and we simplified using these pre-established relationships down here so that all the dimensions work out, and from this we solved to obtain the angular acceleration of the hoop is equal to 1/8 times g over r. From this, we replugged in back into the kinetic equations to find the components of acceleration at point B. This acceleration at B is equal to g over 8 in the I direction plus g over 8 in the j direction. This makes sense with our predetermined sign convention, which follows the right-hand rule of x to the right, y positive down, and clockwise positive for moments.